How to accurately estimate test-with-test reliability. First of all, what is test-with-test reliability? In neuroimaging and psychometrics, there are two types of generalizability. Sometimes we're interested in the population effects. Suppose we have an experiment with two conditions, congruent versus incongruent. So at the population level, we're interested in generalize from the specific subjects to a hypothetical population and from the specific trials for each condition to the task or the condition at the population level. But for test-with-testability, the focus is different. We're interested in individual differences. By individuals, we mean subjects. So we know each subject is unique in the sense that when we compare each subject's brain response or some behavior related to the population average, each subject's effect is different. Some subjects are stronger, some of them are weaker related to the population average. But we hope to find the subject's response are consistent in the sense if we repeat the measurement, they would show similar pattern. So for those subjects respond stronger, when we repeat, we would see similar patterns. So that's what we call reliability. So it's sometimes we call it agreement, sometimes we call it consistency. Traditionally, test-with-test reliability is quantified through the notion of intra-class correlation. There are two popular types. One is called absolute agreement, ICC-2.1. The second popular one is consistency, ICC-3.1. But here we have to focus on the second type, consistency, ICC-3.1. There are many applications in neuroimaging and psychometrics. For example, we can use the notion to check the scanner reliability or behavior data or neuroimaging task-related data. Now we want to intuitively to assess reliability based on some data. For example, in this case, we have 20 subjects. Suppose we have measurement from two different sessions, the blue one and the red ones. So during the first session, the blue ones, we have the population average, which is indicated through the dotted horizontal line. So related to that population average, those 20 subjects, they vary, right? Some of them are higher, some of them lower. During the second session, similarly, those 20 subjects are usually different from the population average, which is the dashed red line. So what is reliable? Well, for each particular subject, during the two sessions, their effects are different from the population average, but we expect to see the consistency. That means the two values from the two sessions should be, most of the time, if they are reliable, should be either both higher or lower. So among those 20 subjects, most of them are consistent in the sense that they are either above the population averages or below. So that is the case. So in this case, the reliability is really high, 0.85. But we do have strong population effects in this case. How about this one, the second case? Well, the population effects for both sessions are virtually zero, right? But that doesn't mean we don't have high reliability if we use the same criteria to judge the individual subjects' effects. So most of the subjects are either above the population average or below. So similarly, the reliability is relatively high, 0.85 in this case. How about the third case? Well, we still have pretty much the same population effects as the first case. However, for most of the subjects, the first session and the sixth session have different relative effects. So most of the subjects are either one of them above, one of them below. So the variability is pretty low, close to 0 in this case. The last case, population effects are 0 for both sessions. How about the variability? Similar to the third case, because most of the subjects, their two values are across the population average. So the variability, again, is pretty much 0. So we have 4 scenarios. Pretty much it's a 2-by-2 factorial structure. So that means the individual differences, first of all, are related to the population average, but they're independent of the population average. So that means sometimes the population effects are high. That doesn't say much about the variability. The variability can be high or low. On the other hand, if the population effects are weak, that doesn't say anything about the variability either. So the variability can be high or low. So typically in neuroimaging and psychometrics, data structure is like this for test with test variability. So we have five hierarchical levels. At the top, we have the population. So then we recruit some number of subjects. So that's the second level. The third level, each subject goes through 2 sessions. The fourth level, during each session, we have 2 conditions usually. So suppose we have inhibition test, we have congruent versus incongruent. Those are the 2 conditions. For each condition, we have some number of trials. So those trials are the lowest level. So those are the 5 levels. We use 4 indices to indicate those 4 levels. The top level population, we don't need the index. So we have the raw data in neuroimaging. That the data is basically the beta values at the trial level. So again, we use 4 indices to indicate the hierarchical structure of the data. So for test variability, conceptually, it's just the correlation value between the 2 sessions. Most of the time, we're interested in the contrast. Suppose we have congruent versus incongruent. We want to say the difference between the 2 at the condition level. Occasionally, we may be interested in the average between the 2 conditions or the individual conditions. How is the traditional ICC value is calculated? Well, there are 2 pre-processing steps involved. So we aggregate the data. So with the data with 4 indices, first of all, we average across the trials for each condition. So now the trial indices disappears. Now then, we subtract the 2 conditions of their averages. So after we finish the aggregation pre-processing 2 steps, then we have the data. Now the data is just 2 indices, one for the 2 repetitions, the second one for the subject. The corresponding modeling framework, we can conceptualize as 2 factors ANOVA, or as a linear mixed effects model. So we decompose the data at the condition and the subject level to 3 components. One at the population level, that's for each session, we have the population average. Then for each subject, have this deviation. Right? Lastly, we have the residuals, which we can interpret as the interaction between session and the subjects. For the second and third components, there are varying effects. So we make assumption. Basically, it's the Gaussian distribution, and there are variances associated with the 2 distributions. The traditional ICC can be interpreted as the correlation between 2 sessions. Right? So that's the basic Pearson correlation. We can also interpret it as the ratio of the variance. Basically, it's the cross-subject variability relative to the total variance. So that's the ICC 3.1. What are the 2 variances? Well, it appears to be the case that the one is for the cross-subject variance, the other one is the residuals. But that's there are subtleties associated with those variances. That's why we have the problem with the traditional consistency. Well, empirically, in the literature, in recent years, we see that for both psychometrics and the neuroimaging, the ICC values are pretty disappointing. Right? It's mostly unreliable. So what's going on? Well, if we take a closer look of the modeling framework of the traditional ICC, there's a missing component. What is this? Because of the aggregation step, 2 steps, then there's the missing component is the trial effects, right? So we pre-process the data. So in the modeling framework, either the ANOVA or linear mixed effects model, we don't see the trial level effects. However, if we go through the probability theory, that doesn't mean the cross-trial variability disappears. It's still embedded in the model. We don't visually see it. That doesn't mean it will go away. It will not. That's why the problem with the traditional ICC is contaminated, because there's a hidden cross-trial variability is not explicitly accounted for. That's the fundamental issue. So we propose a way to resolve the issue. The idea is to explicitly to model the trial level effects without any pre-processing step. So the idea is the test with test reliability should be independent of trial level effects. But how do we achieve that? Well, the idea is to construct a model that as accurately as possible to reflect the hierarchical structure of the data, right? So as close as possible to the data generated mechanism. Hopefully, with that more accurate hierarchical structure, we would be able to resolve the issue. So I want to emphasize that the traditional ICC, there's nothing wrong with the conceptualization aspect, because it is the correlation between the two sessions that we care about. So from the concept perspective, it's perfectly fine. It is the modeling framework that is the fundamental problem, because it doesn't reflect the data structure as accurate. So again, let's refresh the traditional modeling framework of the ICC. So we have the data, right? But the data is only at the condition level, but not at the trial level. So that's the starting point. So we want to build a model with the raw data at the trial level. So we assume the data follow Gaussian distribution with a mean and a variance. The variance, sigma 0 squared, that in blue is the trial level variability. So the mean for the Gaussian distribution, we decompose that into 4 components. The first 2 components are the population effects. We have the average between the 2 conditions, then the difference between the 2 conditions. So that's population level. That's usually, we decouple them from the subject level and the trial level effects. So the second and the third and the fourth components are the subject level. So the third one is the average between the 2 conditions for each subject. The fourth one is the contrast between the 2 conditions for each subject. So for the third and the fourth one, they are varying. So that's why we need to make an assumption about the distribution, Gaussian distribution, for each of them, because it's a bivariate. So we have the variance covariance structure. Within that matrix, the correlation value is what we're looking for. So for the third component, this one, that's the average between the 2 conditions. The correlation value is the test with test variability for the average between the 2 conditions. But most of the time, we're interested in the contrast, not the average. So that's the correlation value in the second variance covariance matrix for the fourth component in the modeling framework. So those are 2 raw values are our focus. So we still maintain the same definition of test with test reliability as the traditional ICC, but the modeling framework is different. That's because now the trial level effects are explicitly accommodated within with the variance for the residuals in the overall distribution assumption. So with that, now this is the hierarchical modeling framework. There are two different ways to see this modeling form. One is still within the traditional statistical framework, is linear mixed effects model. The second perspective is the Bayesian multi-level model. The two different ways, they're different from numerical perspective and also from philosophical perspective. We'll come back to their subtleties later. So with that hierarchical modeling framework, now let's re-evaluate the traditional ICC. Immediately, we'll see why it's troubling with the traditional ICC, because now the ICC value can be expressed as a proportion of the true variability. That proportionality is less than 1. And there are two parameters. The first parameter is in the denominator is the trial level, m is the trial sample size. The second one is RV squared. What is that? That is another ratio. That ratio is the cross-subject variability relative to the cross-trial variability relative to cross-subject variability. So that shows the relative magnitude of the cross-trial variability. So those are the two parameters and two important players for the why the traditional ICC is underestimated. That's one reason. Another reason, even later on, when we discuss the hierarchical modeling, those two parameters are also important. Not important about the accuracy, but important about the uncertainty, the standard error, or how spread out the reliability is. So those two parameters are important, not just for the traditional ICC underestimation, but also for how accurate we'll get the reliability estimates. So now this gives us a new perspective. And also I want to say that the subject sample size, of course, is important, but it doesn't have impact on the underestimation. So if you can increase the number of subjects, but that would not solve the traditional ICC problem, you would still get underestimated ICC. So with this realization, we can make adjustment for the traditional ICC, because the reason is because we realize now the traditional ICC is troubling because their cross-trial variability is not explicitly accounted for. So we can, in the traditional ICC formula, we can remove that component. That is this green part in the denominator. So once we remove that component, then theoretically speaking, that would be a reasonable adjustment. Later on, we'll use simulations to validate this adjustment. So now we have three frameworks. So we have the traditional ICC that now, based on the new modeling framework that it characterizes the data hierarchy, the traditional ICC tends to underestimate. So that the amount of underestimation depends on the number of trials and also depends on the amount of cross-trial variability. So later on we'll see how those two parameters play the crucial role. Computational-wise, the tradition is very simple, right? Just calculate the correlation, or you use the variance ratio. So it's pretty straightforward and simple. But another problem is usually we don't. It's difficult to get the uncertainty about the ICC. So if you read the literature about the ICC reporting, you usually only see their uncertainty, like you only see quantile intervals, you only see standard error estimates. Right? So, but we know in statistics, whenever we get an estimate, there's some extent of uncertainty associated with each estimate. But that's not, at least it's difficult to obtain that for ICC. The data distribution, the traditional approach usually we probably stuck with the Gaussian distribution. And if the measurement has error, that is the case for the neuroimaging, the trial level response, the beta values we estimated. It's not a direct measurement. So whenever we have estimates, there are uncertainty, which is the standard error for each beta. But those standard errors cannot be directly incorporated into the traditional modeling framework. So there's a program for voxel-wise analysis and also for RI-wise analysis too in FNE 3D ICC. So that has been around for several years. So the second framework is the hierarchical structure we just discussed, but that's still the statistic, traditional statistic framework, linear mixed fixed modeling. So this is most of the time it should be accurate, but the problem is sometimes we have numerical failures due to pathological situations, like when the ICC value is uncertain and when the values get close to the boundaries, then we may encounter some problems. Computationally speaking, it's feasible. Usually, I mean, it's for whole brain analysis, you can done within hours. But we still share the same problem with the traditional ICC in terms of uncertainty information. Usually, it's difficult to obtain. Distribution assumptions are pretty much limited to Gaussian. And also, it's difficult to incorporate the measurement errors. In FNE, we have the program 3D RMER to deal with voxel-wise and RI-wise analysis to adopt this hierarchical modeling structure. Lastly, we have the third platform, which is Bayesian multi-level modeling. The opinion of aspect for the Bayesian framework is the accuracy. So it's relatively accurate and numerically it's robust. But the only downside is the computation cost is pretty heavy. But we have other advantages like uncertainty, pretty easy because we have the posterior distribution. Assumption about the data, it's pretty flexible. You can pretty much adopt most of the distributions like student t, log normal, exponentially modified Gaussian, so etc. and etc. Measurement error is pretty easy to accommodate whenever we have the input data is not direct measurement, so the uncertain information can be accommodated. So we do have a program, TRR, standing for test with test reliability, that can be used for ROI level reliability estimates. So with the new framework that they are characterize the hierarchical structure of the data, now we want to perform some simulations to validate the theoretical deviations, and also we want to gain some insights about the comparison between traditional ICC and the tested with test vulnerability. And we want to also gain some insights about the dependence of the parameters, such as trial and subject sample size and the cross-trial variability. So the plots, there are a lot of information. We want to be able to get into details, but we want to summarize the simulation results. First of all, the simulations do confirm the ICC underestimation. The amount of underestimation is basically that linear dependence we discussed a little bit earlier. So that's the simulations do confirm that the sample size is a big factor. So smaller sample size, we're going to have severe underestimation from traditional ICC. Similarly, if we have large cross-trial variability, that's the ratio RV. If the cross-trial variability is relatively large compared to the cross-subject variability, then the underestimation is also severe. The subject sample size does not have impact. We confirmed that too. Lastly, the theoretical adjustment, if we move the cross-trial variability from the denominator of the ICC formula, we would be able to make a corrected estimate. So that is conceptually satisfying, but practically it's not much use. because we cannot directly get the trial level effect estimates under the traditional modeling framework. In addition to the confirming the ICC underestimation, we also gain some insights about the test with reliability based on the hierarchical modeling framework. That's because we're not just getting the estimate of the reliability, we also need to check the uncertainty, which is, the distribution or the standard error of the reliability. So there are three major players. One, it's basically the two sample sizes, trials and subjects, and the cross-trial variability, relative magnitude. And the trial sample size plays a little bit more important role than the subject sample size based on the simulation results. Since we have three frameworks now, the ICC, traditional framework, linear mixed effects modeling, and the Bayesian multi-level modeling. So those are three frameworks. But the linear mixed effects modeling approach still need to be problematic is because we may have numerical failures that is shown in the numerical results. And as I mentioned earlier, there's no uncertainty information about the reliability, and the distributional assumption is limited to Gaussian, and there's no way to incorporate the measurement errors. So now let's look at the whale data set. This is the Franker task. With this data set, we have 42 subjects. Each subject went through 2 sessions. So Franker task is an inhibition task with 2 conditions, congruent versus incongruent. So in the scanner, each subject make assessment about the arrow in the middle. How is that either congruent or incongruent with the rest of the arrows? So then you push a button, you make a decision. So there are 270 trials for each of the 2 conditions. However, the subjects, understandably, they may make mistakes. So close to 1/3 of the trials, the subject didn't make the correct choices. So in the end, the whale data for each of the 2 conditions will have roughly 190 trials, correct responses. So that's the data we have. So we go through the typical route. At the subject level, we perform regression analysis at the trial level, not at the condition level. That means we create 1 regressor per trial. So in the end, each trial will get a beta value. With that data, then we calculate the traditional ICC. So using the FNE program 3D ICC. So here I show 3 slices in the brain. The color bar is split at the 0.5. So below 0.5 is the cold color, bluish. Above the 0.5 ICC value is the warm color from yellow to red. So as you can see, most of the brain regions are pretty much unreliable based on the traditional ICC. Only a few regions that slightly above 0.5. So the conclusion is not really reliable for most brain regions based on the traditional ICC. But how about the hierarchical modeling approach? Well, under that framework, we have 2 different numerical ways. One is we use the linear mixed effects modeling approach. In that case, I'm not showing the results. The reason is the results just not much interesting to show. That's because most of the voxels in the brain failed because of the numerical issues. So as I mentioned earlier, this modeling framework, theoretically speaking, should give us accurate estimates, but the problem is it's a numerical thing. So there's not we can do about it. How about the Bayesian approach? Well, I cannot show you the results either. The reason is the Bayesian computationally cost is pretty heavy. It's just not practical. So we don't have results to show with the Bayesian approach. However, we can use the Bayesian approach and apply to some number of regions. In this case, we tried with 12 different RIs using the affinity program TRR. So we run this Bayesian modeling approach program on each of the 12 RIs. And we also make slightly different assumptions. Instead of Gaussian, we assume the data follows student distribution. The underlying reason is because since we estimate the brain response at the trial level, there's a lot of outliers actually. So because of that, we use student distribution instead of Gaussian to accommodate those outliers. The second unique thing about the Bayesian approach is we also incorporate the standard errors of those individual betas into the Bayesian model. The reason is the beta values at the trial level are not directly measures. They are estimated through a regression model. Because they're estimated, there are uncertainty, which can be conceptualized as the standard error. So we can provide those standard errors as input for the Bayesian model. So those are the two unique things, the student distribution and the standard error for those beta values as part of the input for the Bayesian modeling framework. So here, the two rows shows the total of 12 RIs. This is a little bit different from the traditional ICC in the sense that we're not just showing one value. We're showing the distribution, the histogram of the reliability estimates. So for each of them, we show the distribution. So there's a peak, right? We call it mode. That basically we call the highest density. So that we can use that as sort of like similar to the traditional studies like average. But in this case, we call it mode. That's where there's a most likely region. I'm also showing, in each panel, I'm showing the traditional ICC. So for example, the first RI, this RI, it's peaked around probably 0.75-ish, but the traditional ICC is just 0.12. So we can see some substantially amount of underestimation. And also I'm showing the last row in the panel is the cross-trial variability is 69. What does that mean? That it means the cross-trial variability is close to 70 times higher than the cross-subject variability. That is something we need to keep in mind. Why is the cross-trial variability so high? We'll come back to that immediately. But that is an important factor why the traditional is underestimated, and also why the distribution of the reliability is so diffuse. So compared to the previous slide, I showed the 3 slices of the brain images of the ICC value. This is the total different. We do say some regions have relatively high reliability. For example, the last 2 regions on the second row, they are pretty reliable, and the distribution is pretty narrow. That means pretty precise. Some of the regions, like the first one and the last 2 on the first row, and the second one on the second row, their peak are relatively high, but the distribution is pretty diffuse. So that tells us something about something. We do have the relatively high reliability, but it's some extent of uncertainty. Why is that? That's probably 2 reasons. One is the number of trials are limited, even though we have 190 trials for each condition. And another player is the cross-trial variability, the really high. For example, this region 68, this region is 53. For those 2 regions, the cross-trial variability ratio is 22, pretty high. Why is that? Well, this is the crucial thing. So in addition to the number of trials, the cross-trial variability is important. Why? And why it's so high? Well, we have the numerical data, but fundamentally, that says something about the brain. There are mounting evidence shows that the cross-trial variability is something. It's something fundamental. There are some papers in the literature that indicate that the trials is not just it's the brain response relative to the baseline. In other words, the baseline is not just the horizontal. The brain is not static. There are always something ongoing in the brain. So the individual trials basically ride on those waves. That's their currently understanding about why we have such a huge amount of cross-trial variability versus the cross-subject variability. So based on the data sets we have investigated, the ratio of the cross-trial variability relative to cross-subject variability is about 10 or even above. So here I'm showing you some results. For this particular data set with the flanker task, so those 7 slices in the brain shows the amount of cross-trial variability. So again, the cross-trial variability ratio is the factor of the cross-trial variability relative to the subject variability. So the cold color shows the regions in the brain that the cross-trial variability ratio is less than 50. The warm color is about 50. So the important regions for this relative to this particular data set and the task is those blue regions that are around 10 or around 20. I mean, some regions are even higher, but most of the higher ratio regions are in CSF and white matter. So on the lower left corner is the histogram of the ratio. So it peaks around 20. So that means most blue regions are in the neighborhood of 20-ish. And also on the lower white color, it shows one brain region. That's the trial level effects. So because this combine both conditions, congruent and incongruent, so there are over 300 trials. You can see there's so much amount of fluctuations from trial to trials, even though there's just 2 types. Oh, actually, this is just one condition. I believe this is the incongruent condition. Even though this is the same condition, the fluctuations are so large. So this is something fundamental about the brain, as I mentioned earlier, because this Wolf paper, recent paper discusses about the reason for such a huge amount of cross-trial variability related to cross-subject variability. So let's summarize our discussions. I want to re-emphasize again, there's nothing wrong about the traditional SSA in terms of concept. So it is the correlation between 2 sessions. That's what we care about. So the concept itself is what we are interested in. There's nothing wrong about the concept. The issue is about the modeling framework. So the problem with the modeling framework is we can discuss from 3 different perspectives. One is accountability. Because the traditional framework, there's no position for the cross-trial variability. The trial level effects are not characterized. So that's one angle to visualize, to conceptualize the problem. The second aspect is the sampling. Based on the probability theory, like a law of large numbers, conceptually, if we have an infinite number of trials, then the traditional framework would work. Well, I mean, infinite, that's not reasonable, but how about large enough? How large? Well, probably would be, I would say, in order for hundreds or even thousands. In that case, maybe we would not have the ICC underestimation problem, but in reality, the real number of trials usually implemented in FMI or psychometrics is not that large. So that's why we have the underestimation problem. So that's the second perspective. The third one is the quantitative variability. So that basically involves why the quantitative variability is so huge. If the quantitative variability is in the same order of cross subject, that means the ratio is around 1 or less, then we would not have the underestimation problem. The traditional ICA the modeling framework, the formula would be fine. We would not have the discussion today. But unfortunately, quantitative variability is so large. That is something fundamental about the brain response. So it's large to the extent it's at least 10 times larger than the quantitative variability. So that's another perspective to discuss the ICC problem. So quantitatively, the traditional ICC underestimation can be expressed as the linearity of the true ICC value, variability value. That proportionality, that proportion is less than 1. That's because there are two parameters, trial sample size and the cross-value ratio. So those two parameters basically play the important role for the underestimation. They also play important role for the variability uncertainty as well. Even if we adopt the hierarchical modeling, those two parameters are still important. On the other hand, the subject sample size doesn't play any role about the underestimation. It does play a role for the uncertainty of the variability estimate. Another aspect of the ICC issue is that usually in the literature, we don't see uncertainty report. That's because it's difficult to obtain such uncertainty information. So here we suggest a hierarchical modeling approach is a better one to more accurate to characterize the data generated mechanism because we directly account for the trial effects. So that means at the subject level in fMRI data analysis, we should estimate the trial level beta values, not like the common practice. We create one regressor per condition per task. Instead, we create one regressor per trial. So we obtain the trial level effect estimates. So with that, we build this hierarchical model. So we, in the end, will have 5 levels data structure. So then we also discussed that even with the hierarchical model structure, now the important aspect is about the uncertainty. We're not just obtain one value for the variability, we also need to estimate the uncertainty. Now the uncertainty can be expressed as the standard error, but that's not accurate because the standard error is not, its distribution is not symmetric. So under the Bayesian framework, we express the uncertainty as the distribution of the estimate. So we get the full distribution to get an accurate estimate about the uncertainty. So even under the hierarchical modeling framework, those 3 parameters are still important. The quantitative variability ratio and the two sample size. They also play an important role. So that means when you design experiment for test retestability, it's the best to increase those two sample size as much as possible. So based on the current empirical data, I would say the number of trials is the more important player. Probably it's better to at least in the hundreds. In terms of quantitative variability ratio, that's not under our control. There's nothing we can do about it. It's just the reality we have to face. So lastly, I just summarize those 3 modeling framework. The traditional ICC, the issue we discussed is major because of the underestimation, because we can't directly account for the trial level effects under the ICC modeling framework. The linear mixed effects modeling framework is computational feasible, but the problem is we usually encounter numerical failures due to pathological issues. So it's better to adopt the Bayesian framework. We get a better estimate and robust numerical solvers. But the big hurdle is currently we can't do that at the voxel level because of the computational cost. For all the 3 modeling frameworks, we have the programs available. you can choose per the condition or the situation. Lastly, I want to thank my collaborators and colleagues, and also thank you for your attention.